Today's event features an award-winning project within the Munitions Response program area on decision support tools for munitions response performance prediction and risk assessment. Dr. Lawrence Baran will be the only presenter and will pause halfway through his presentation to entertain questions from the audience. We will conclude the webinar with a second Q&A session at the end. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A sessions. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Dr. Herb Nelson, who has been serving as the CERTUP and ESTCP Program Manager for Munitions Response since 2007. In addition, Herb is the Executive Director of CERTUP and ESTCP. Prior to joining the programs, Herb was a research chemist at the Naval Research Lab in Washington, where his work focused on the detection and classification of buried UXO. Herb, I'd like to turn it over to you now.
Thank you, Rula. I appreciate it. So welcome to everyone. I'd like to add my welcome to Rula's welcome. And we're particularly pleased, of course, because we're in the part of the series where we're talking about the award winners from last year of Projects of the Year. So we've got a really good lineup, these 4 or 5 that we're in the middle of. So today as a quick introduction, of course, CERTUP, many of you know, is the Strategic Environmental Research and Development Program. It was established by Congress quite a long time ago in fiscal 91. And it's a DOD, DOE, and EPA partnership. CERTUP is really a research and development program spanning from, as you see at the bottom, fundamental research through advanced technology development. The next slide, please, Rula. ESTCP, which is the sister program, is the Environmental Security Technology Certification Program. And it, in some senses, is the logical follow-on to CERTUP, where we take the technologies developed in CERTUP or developed elsewhere and demonstrate them at DOD facilities. And the question we're trying to ask in an ESTCP project is, how well does it work and at what kind of cost savings or efficiency increases we can get from new technologies. And we're always looking, as this bottom bullet says, to promote implementation by facilitating both regulatory acceptance and acceptance by people at defense installations. So the technology transfer is a big part of an ESTCP project. Next slide, please. So the 2 programs are managed out of the same program office. We divide ourselves into 5 program areas, as you see on this slide. Energy and water is only in ESTCP. The other 4, environmental restoration, munitions response, which is, of course, the subject of today's webinar, resource conservation and resiliency, and weapon systems and platforms are in both ESTCP and CERTUP. Next slide, please. So as I said, this is a munitions response project that we're talking about today. Munitions response has classically had a component of munitions on land and munitions underwater. We are really coming to the end of the munitions on land, and in fact, Lawrence may know better than I, this might be the last of the land projects. But it was a good one because it was the award winner this year for, in fiscal 16, I'm sorry, in 16, it was the award winner for Best Project of the Year. Next slide, please. So as you see on this list of the upcoming webinars, we're right in the middle of the award-winning projects. On February the 23rd, we'll have Resource Conservation and Resiliencies Project of the Year winner, and then on March the 9th, we'll have the winner from the Environmental Restoration area. And then there is the webinar schedule for the rest of the early spring. And then there'll be, of course, on our website, if we go to the next slide, you'll see the link. You'll see on our website that, in fact, we've pretty much settled the webinars through the end of the calendar year. They're not all completely locked down, but as they appear and as they're settled, we will put them on the website there. You can always check back to see what's coming up. Okie doke. So the final thing I'd like to talk about is another thing that I'm very pleased to discuss with you. We have gotten approval and are well in the planning of the CERTUP and ESTCP Symposium, It's been quite a hiatus since the last one we were able to have one of these, but now we're going back again. It's scheduled for our standard week, which is the week after Thanksgiving. This year that will be November 28th through November 30th. It is at the Washington Hilton Hotel, or will be at the Washington Hilton Hotel in D.C., which is the hotel we had it at the very last time we had a symposium. We've made the announcement. The hotel is all booked. The registration page will be active soon, and of course, when it is, we'll do a blasto email so everyone will know. So I certainly encourage you all, if you're able, to attend this. It was quite a good event in its last life, and we wanted to come back even stronger than it did before.
Thank you so much, Herb. It is now my pleasure to introduce today's speaker, Dr. Lawrence Duran, who is a research geophysicist with Black Tusk Geophysics in Princeton, New Jersey. Dr. Duran specializes in the development and application of statistical algorithms for the classification of unexploded ordnance. He has served as the PI of multiple CERDA projects, and his current work focuses on the detection and classification of deep UXO and underwater UXO. Dr. Duran completed his master's and doctoral degrees both in geophysics at the University of British Columbia. And with that, I turn it over to you, Dr. Duran.
Great, thanks, Rilla. Thanks for the nice introduction. So as was introduced today, I'm going to be talking about decision support tools for Munitions Response. And this is work that was carried out under CERDA project MR 2226. So today I'd like to focus on some of the highlights of this project. And I'll first give you an overview of advanced geophysical classification, and then discuss our work on detection with advanced sensors. And so first, I'd like to discuss some work on threshold modeling for target detection, and in particular, talk about some software tools that we've developed to do this analysis for advanced sensors. I'll also touch on some applications of threshold modeling to selection of an optimal time channel for target detection, as well as dealing with high-density areas where there's a lot of metallic clutter present. And then in the second part of the webinar, I'm just going to briefly discuss some work that we did on risk assessment. And in the context of Munitions Response, what we mean by risk assessment is looking at ways to test decision points and test decisions that we make during the classification process. Okay, so this work has really been driven by the development and demonstration of advanced electromagnetic or EM sensors under the CERDIP ESTCP program. On the top row here, I'm showing the geometries of 3 of these advanced EM sensors with transmitters indicated as black dashed lines and receivers as red solid lines. And these sensors can all be deployed. We can see that they all have multiple transmitters. So the man-portable vector sensor on the right that I've shown can have additional transmitters. And the sensors all have multiple receivers, so the red solid lines. And so what these multiple transmitters and receivers give us is data that can really support the advanced processing techniques that I'll be discussing today. So regardless of which advanced sensor we use for advanced classification, we're always following the same workflow. And I'll just very quickly review the processing and data acquisition workflow that we go through. So the first step, of course, is to detect buried targets, and we do this by acquiring a full detection map, as shown on the right. And you can see in the inset plot in the middle here some of the anomalies that we detect. And so this detection stage is increasingly being done with advanced sensors, such as the man-portable vector sensor or the TEMTADS. And I'll talk about a little bit more about the advantages of advanced sensors for target detection later in the talk today. So once we have our detection data, we can then pick targets for further interrogation, and I've highlighted in the inset plot some potential target picks, and I'll be discussing this step in some more detail today. Picked targets are then revisited for cued interrogations. So at this step, we take a stationary advanced sensor and we position it directly on top of each pick location and collect data with the sensor in a stationary position. So this gives us really high quality data because the sensor is not moving. We don't have to contend with any positional errors. And so we can really use our cued interrogation data to do characterization of our detected target. So we do that characterization in the feature extraction stage. And at this step, we use modeling and inversion to estimate for each target a location and depth, orientation, and polarizabilities. And I've highlighted the polarizabilities here because they're really intrinsic parameters that allow us to distinguish between unexploded ordnance, UXO, and non-UXO, so metallic clutter. So UXO are typically characterized by slow decaying polarizabilities, as we see at the plot on the bottom left. L1, L2, and L3 are our polarizabilities. And this is in contrast to non-UXO, which are typically slow decaying. So, pardon me, non-UXO polarizabilities are typically fast decaying. So it's this kind of information in the polarizabilities that is useful for classification, and the polarizabilities are really related to size, shape, and material composition of the metallic targets that we're detecting. In the final classification stage, we can match the estimated polarizabilities for each target with a predefined library of polarizabilities for targets that we expect to find at the site. And this gives us an ordered dig list, which I visualized here, showing on the left the decision statistic or a mismatch between the estimated polarizabilities and our library polarizabilities. And then you can see here in the middle of each column, we have the estimated polarizabilities for each target. And then on the right, we've got an image of the ground truth that we get as we're excavating our targets. So you can see initially in our dig list, we're primarily finding seeded items. And then down here, you can see a munition item that we found. And then on the far right, as we jump ahead in our dig list, we're primarily finding non-hazardous metallic clutter. And so an important decision that we have to make at this stage of our workflow is when to stop digging. And I'll talk a little bit more about that decision and how we can test that decision as part of our workflow. Okay, so I'd like now to turn to some of the specific work that was carried out under this project. First, focusing on detection and target picking. So as I mentioned, newer advanced sensors are really increasingly being used for detection, and this is really because they provide us with higher resolution and longer measurement windows relative to conventional EM sensors. So on the left here is a detection map acquired with a conventional EM sensor, compared with the advanced metal MEPR sensor in the middle and the right. And we can see that the metal mapper images are less blurry relative to the conventional sensor on the left. And it's this higher resolution that really allows us to resolve closely spaced targets in our advanced sensor data. Additionally, at this late time channel in our metal mapper data, if we focus on the top right corner here of our detection map, you can see that at late times we can really resolve some individual anomalies which are not really apparent at earlier times for the metal mapper, or indeed for the EM61, which is very saturated. So this late time information on the right is really useful for identifying slow decaying targets that may be large UXO, as well as screening out some fast decaying clutter from our target picks. So while advanced EM sensors have many advantages over conventional sensors for detection, for practical implementation of detection with advanced sensors, there's a number of questions that we need to answer on the processing side. So first and foremost is how should I pick targets with my advanced sensor data? And we really want to exploit as much as possible the information that we're getting with our advanced sensor data. And then secondly, related question, if we're just picking on a single time channel, is there a time channel that's really optimal for detection of the munitions that we're looking for? Number three, how deep can we detect and classify with advanced sensors? And then finally, where can classification be applied? Or I think more accurately, are there locations at a site where there's really a high density of clutter and we can't really resolve individual target responses in order to do classification? So as part of this project, we've tried to address some of these questions, and I'd like to now proceed to the first question, which is how should I pick targets? So under CERDIP, a number of target picking approaches, which are being termed informed source selection methods, have really been developed to address target picking with advanced sensors. And these methods really aim to use modeling and inversion to pick and screen targets. And I think there's really two complementary approaches to informed source selection. On the left here, we can first pick targets in the data using a detection threshold, and then follow these initial picks up with an inversion. And the purpose of the inversion is really to refine our target locations, resolve some closely spaced targets that might be present at the site, and then finally to possibly eliminate some fast decaying targets, so to screen fast decaying targets from our initial target list. Alternatively, we can start our informed source selection with a fast inversion of all the data to give us an initial indication of target locations, and also to do some initial screening. And so this is an approach that's been developed under some other CERDIP projects. So methods such as dipole filtering and dipole clustering use a fast inversion of all the data. And then these initial inversions still have to be followed up with a full inversion, in particular multi-object inversion, because we're always concerned about, again, resolving closely spaced targets in our data. So today I'm really going to focus on the first approach to informed source selection, which is identifying targets first using picking on it with a detection threshold. But I would emphasize that the two approaches to informed source selection are really complementary and can be used for quality control of each other. So for example, we could use we could quality control picks from an inversion-based method, such as the dipole filter, with picks generated using detection thresholds on the data. So any threshold-based picks that are screened out by the dipole filter could be further investigated as part of a quality control process as we go through our classification workflow. So I'll talk now a little bit more about detection thresholds and how we can use them as part of informed source selection and understanding detection with advanced sensors. And so the conventional approach, again, to target picking has been, even when we're working with sensors such as the EM61, is to work with gridded images or profiles and pick peaks above a threshold. So I've shown here a profile acquired with an advanced electromagnetic sensor over 3 buried industry standard objects, or ISOs, at different depths. And you can see multiple profiles are plotted here because we're measuring with multiple receivers, and some of those receivers can give us both a positive and negative response. So again, the simple approach to target picking is to predict some minimum threshold that we expect for our observed anomaly. So often we work with the Z component data. We predict or model a threshold, and that would be indicated by the dashed line. Any anomaly that's above the threshold is then going to become a target pick, or an initial target pick. And we can see here that the detection threshold depends, of course, on target depth. So deeper targets are going to produce lower amplitude responses. And target orientation also plays a role. So typically the maximum and minimum amplitude responses of a target correspond to vertical and horizontal target orientations, respectively. So how can we calculate a detection threshold? In order to model the detection threshold, we have to specify a number of extrinsic survey-related parameters. So of course, the first thing that, as we saw in the previous slide, is the depth of a target. And this is usually specified as some site-specific maximum clearance depth for the targets of interest that we're looking for at a site. So we always want to consider the worst case scenario when we're modeling our detection threshold. So we consider a target at that maximum clearance depth. Secondly, we also have to consider survey parameters such as line spacing and sensor height, and I'll talk a little bit more about the effect of line spacing in a few slides. And then finally, target orientation. So we're always concerned with target orientation relative to the sensor, and again, typically horizontal targets are going to give us the minimum amplitude response. And then, of course, the final modeling input is the intrinsic polarizabilities, as we've seen before, that are specific to each ordnance type. And these, of course, can vary over orders of magnitude and have a really big impact on the observed data amplitudes that we're modeling for our detection threshold. Okay, so given these extrinsic and intrinsic parameters, we can then model the dependence of the detection threshold on a specific input. So for example, here, the detection profile on the right is showing the dependence of the detection threshold on the location and orientation of in this case, a 37 millimeter projectile at 30 centimeters depth below the TEMTADS 2x2 sensor. So on the left here, we've got, again, the geometry of that sensor. And in this analysis, the target is horizontally oriented, and its nose is either pointing along the track of the sensor, so along the X direction here, or across track. So when it's along the track of the sensor, we get this green line for our detection profile. And if it's across the track of the sensor, we get the blue line in this detection profile. So now if we pass over a target that's directly beneath our TEMTADS 2x2 receivers, as indicated by the blue dashed line, then we obtain a minimum threshold response for a target in the cross-track orientation. So the minimum response on the right here corresponds to the cross-track orientation of a horizontal target. So if you're familiar with the EM61 sensor, you're used to thinking about horizontal cross-track orientations defining the detection threshold, and that's analogous to this case here. For the TEMTADS 2x2, however, the worst case detection scenario is really going to correspond to this case indicated by the red solid line. So we're passing, the center of the array is passing directly over the target location. And the minimum response that we get in that case corresponds to a target in the along track orientation. So the target, the nose is pointing along the sensor track. And it's this minimum on the right here within the footprint of the sensor that is really going to define our worst case detection threshold when we go to pick targets on the data. Okay, so it's interesting, I think, to look at the effective geometry on the detection threshold as well. So we can do the same analysis for the man-portable vector sensor or the metal mapper array as well. And because this sensor has receivers at the center of the array footprint, so you can see here at x equals 0, we have receiver cubes. Because we have those receivers on the right here, the minimum response within the footprint of the sensor is shifted to the edge of the array. So that's, again, now corresponding to the case indicated by the red line, where we're just brushing by a target with our sensor head that's oriented along the track of the sensor. If we tighten the line spacing of our detection survey, then we can raise the detection threshold by effectively decreasing the maximum deviation of the target away from the center of the array. So as we decrease the line spacing, we push that worst case detection threshold in towards the center of the array. And then you can see on the right here that the effect of that is to raise the worst case detection threshold, in this case from about 5.5 to 6 millivolts per amp. So it doesn't sound like a big increase, but in practice, by tightening the line spacing, you can have a big impact on the initial number of target picks that you generate, and that can save you quite a bit of effort and decisions to be made when you're doing informed source selections. So I think I've shown in the previous slides how we can get some insight into where the worst case detection threshold occurs for different sensors based on the different geometry that we're working with. And I think another application, as we've seen for threshold analysis, is in channel selection. So as we mentioned, we can measure much later in time with advanced sensors, and this allows us to really filter out fast decaying clutter from our initial target picks, as we saw here in the top right corner for the metal mapper sensor. However, we do also have to think that if we go too late in time, then the worst case signal to noise ratio of the munitions that we're looking for may become too low. So we have to balance screening out clutter with maintaining a good signal to noise for the munitions that we're looking for. Here's a second motivating example for selecting a time channel. And here we're showing data images with threshold-based picks, the white triangles, when we work with an early time channel and a late time channel. As you would expect, the early time channel is identifying a lot of picks, but most of these turn out to be fast decaying clutter and can be really very easily screened out by picking out a later time channel. So here we reduced from 90 picks to 7 picks, and that really saved us a lot of time and money and effort for our informed source selection and subsequently for our queued interrogation. So people have been thinking about this issue of what channel to use for detection for a long time. What we've done in this project is to try and come up with some automated approaches, automated and objective approaches for selecting a time channel. So here we, in this analysis, we consider a sum of the time channels, and we do a weighted sum of time channels to come up with our detection channel. And here the signal that we're considering in our detection channel is in fact the worst case detection threshold. So what we do is maximize the signal to noise ratio in our worst case scenario. So we maximize the signal relative to some estimate of the noise for our detection channel. So one sec here. So the result of this analysis is a weighted sum of channels that optimizes detection for each target type. Here we, on the left, you can see the polarizabilities for 3 ordnance types. And then in the middle plot, we've got an estimate of the noise standard deviations at each time channel. And then on the middle, or on the right plot here, we have our optimal weightings for a detection channel for each of the different ordnance items that we're looking for. So the intuitive result here is that slower decaying items, such as a 155 millimeter projectile, put more weight at later times, as indicated in this right-hand plot. Whereas detection for a fast decaying fuse is we want to put more emphasis at early times. And so this analysis can help us formalize the selection of time channels when we're doing picking on a single time channel or a sum of time channels. Another analysis that we can do using thresholds analysis is to look at the dependence of the detection threshold on target depth using the response curve. And this really can give us information as to how deep we can detect and classify. So in this plot, we're showing how the detection threshold varies with depth below the sensor for the worst and best case orientations of a 37 millimeter projectile. So again, here the worst case is a horizontal target, and the best case is a vertical target. If we have an estimate of the noise at the site, then we can use the response curve to determine the maximum depth down to which a target can be reliably detected and classified. So usually what we do is we take 5 times the standard deviation as a conservative cutoff, and that's indicated by this black solid line. So if we look at the intersection of our response curve with 5 times the noise standard deviation, here that gives us an indication that we can reliably detect and classify, as a rule of thumb, in this case down to about 45 centimeters depth below the sensor. And in this case, the depth below sensor is including both the height of the sensor plus the depth of the target below the ground. And then one final analysis that we can carry out using detection thresholds is what we call a clearance depth analysis. So in this analysis, we consider the threshold for a prescribed clearance objective. So for example, we might our primary clearance objective might be to find 37 millimeter projectiles at 30 centimeters depth. And given that threshold, then we can predict how deep other munitions at the site will be detected at that threshold. So that can really help us in the early stages of a project as we're building our conceptual site model and understanding how well classification will perform for different munitions items. So the plot on the right here is comparing predicted clearance depths for various items, and the obvious result is that larger items are going to be detected down to deeper depths. And there's a small difference here in predicted clearance depths between the 3 advanced sensors, and this is really a consequence of difference in transmitter sizes, which has an effect on how deep we can detect and classify with an advanced sensor. So in order to transfer some of these analyses to the community, what we've tried to do in this CERDIP project is to develop some software to do a lot of threshold-based analysis and try and understand detection with advanced sensors. So we've developed a free Windows-based application, and this application works with the DoD standardized polarizability library that's been acquired under CERDIP. And so the software has functionality at the moment for both Metal Mapper and TEMTADS 2x2 sensors to do all of the threshold-based analysis that I've presented today. And so for download, if you're interested in obtaining a copy, please contact us, and we will be happy to provide a copy of that software to anyone who's interested. And I'll stop here for questions for the first part of the webinar.
Wonderful. Thank you, Dr. Baran. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions for you. This is a question from the U.S. Army Corps of Engineers. Can you please explain whether a dipole response indicates an anomaly with a length greater than width or diameter?
So for all targets that we detect, we model the response of the target as a dipole. And it's really the polarizabilities that give us some information about the size and shape of the target. So if we look at the polarizabilities, what we see for most munitions items is we have a large amplitude primary polarizability, and then we have a secondary and tertiary polarizability that are ideally for a munitions item are equal. And so equality of those secondary polarizabilities is telling us that the target has a circular cross-section, and then the dominant primary polarizability gives us an indication that it's a rod-like target. So it's really the polarizabilities that we get in our feature extraction stage that give us information about the size and the shape of the targets that we're detecting and classifying.
Thank you. Can you please summarize the benefits of this work in detection optimization? Is it primarily reducing the size of areas designated for digging operations? And if so, can you please provide more details?
So I'll be talking more in the second part of the talk about reducing the area required for detection or for full clearance operations. I think the optimization work that I presented, where we're talking about selecting an optimal time channel, I think that the utility of that is really helping an analyst or anyone who's working with the data to understand what time channel to work with. Often people have a pretty good intuitive sense that you don't want to go too late in time because of decreased signal to noise ratio. But that optimization of time channels can really help you to identify in an objective way what channel to work with. And yeah, I think that's That would be my answer.
Thank you. How does one account for the effect of noise on the detection threshold?
So that's a good question. So we always want to, when we model our detection threshold, we're modeling it in the absence of noise. And then, of course, when we're collecting data at the site, there's always background response and noise introduced due to the motion of the sensor. And so what we typically do is find an area that's in our detection survey that's free of any significant anomalies, and we can use that to get an estimate of the noise standard deviation in our detection data. And then essentially what we do is we adjust our detection threshold to account for the effect of noise. So we would decrease the detection threshold, say by 2 standard deviations of the noise in order to account for the effect of noise on the detection threshold.
Thank you. And how does one get a noise estimate for channel optimization?
Well, again, as I just said, you would look at a quiet area in your detection survey and just look at what the background response is at that location to get an estimate of the noise standard deviations as a function of time.
Thank you. I have a fairly detailed question for you. Has there been any studies on munitions with bent nose spikes, like on the 106 millimeter heat projectile, 81 millimeter mortars with bent tail sections, and BDU-33 with bent tails?
I think I'd push that question to Herb. I'm not 100% sure about that one.
Yeah, so this is Herb that will be happy to answer that one. So studies maybe is too strong a word for that, but we have certainly encountered those kind of bent and misshapen munitions at several of our sites in the live site demo program that ESTCP ran. And we got surprisingly good classification performance on that. The best example was at Massachusetts Military Reservation, where many of the items were missing a significant fraction. There were a lot of low-order detonations that would blow out a quarter or a third or pop off the fins of a mortar or something. And in that case, we had no real issues with classification. So that's a partial answer to your question.
Thank you, Herb. Okay, another question from the U.S. Army Corps of Engineers. Does optimal weighting have 2 variables? Also, does the munitions ISO library contain these weighted values? So I'm going to ask you to respond first, Lawrence, and then maybe Herb can weigh in.
Okay, so does optimal weighting have 2 variables? So you're maximizing, in the analysis, you're maximizing the signal to noise for detection of a target. And so the signal in that case is your detection threshold as a function of time. And your noise is, again, an estimate of the background noise at the site. So those are the two variables that are being input into the analysis, and then the output is a set of weights as a function of time, as I showed, where you're getting an indication of which time channels should be weighted heavily for optimal detection. And then the second question, does the ISO library contain these weighted values? So in the channel optimization, it's very much a site-specific analysis. So you're using site-specific noise to come up with an optimal channel for detection for that particular site that you're working at. And then in order to do this optimization, you do need polarizabilities for the targets of interest that you're looking for, and that, of course, can be obtained from the DoD polarizability library.
Herb, would you like to add anything else?
No, I don't think so.
Lauren's
answered that correctly. Yes, the library is just the polarizability curves. What you do with it, and an example of all these exciting things Lauren's has done with it, are add-ons to the library.
Great. And Herb, can you tell us how one can access the DoD polarizability library?
Yeah, I certainly can, although the answer I'm going to give is going to be necessarily incomplete. It is always will be available through your government program manager when you work on a site. The question is, how much will it be available outside of that channel, and that's still being really worked on. I think the NAOC Technology Committee is going to get a preliminary copy so NAOC members can use, but definitely the most up-to-date version will always be downloaded by your government PM and presented to you at the beginning of any investigation on a site.
Thank you so much, Herb, and thank you, Lawrence. And I'm going to invite you to go ahead and proceed with your presentation, and we'll answer the remaining questions that we've received in the final Q&A. Lawrence? Okay.
Great. Thanks, Rula. So in the second part of the webinar, I'd like to just quickly finish talking about detection with advanced sensors. And here I'm going to be talking about dealing with high-density areas where there's a lot of metallic clutter present. So I've shown here a motivating example from an ESTCP demonstration at Camp Hale, where there was really an extended area outlined in green here with an elevated response in the TEMTADS 2x2 data. So this green polygon was basically, we just eyeballed the area that we decided was going to be excluded from the classification analysis. And if we look in the inset plot on the left, we can see that within that small subset of the area, there's some extended large anomalies, but there's also some isolated anomalies nearby on the periphery that can still be classified and should still be included in the classification dig list. So our goal here is then to, with this analysis that I'll be presenting, is to delineate regions where classification can't be carried out because we can't resolve individual target responses. And then these high density areas are going to have to be fully cleared. Here's a second motivating example from a recent marine classification project. And I've highlighted a couple areas here where there was really a lot of metallic clutter, so a high signal in this image is in purple. And so there was really a lot of metallic clutter present, and no classification was possible. And this is really an important problem in a harbor such as this, where there's a lot of cultural debris, and dealing with cluttered areas is really expensive and time-consuming. So it's something that we really need to think about as we move classification into the marine environment. So we want to come up with some automated and objective ways of delineating these high-density areas. And I'll first talk about how we can approach this problem generically as an image segmentation or a region finding problem. And then talk about some of the different images that we could work with. We can either work with a data-based image or an image derived from inverting the data. So if we consider that inset area from Camp Hale, working with an image of just the data as an example, how can we automatically outline a high density area? The first step is going to be to define a regular grid of pixels. So here we're using a 1 by 1 meter pixels in our grid. And then within each pixel, we can apply a thresholding operation to determine if there's sufficient signal in that pixel such that we would consider that there is metallic clutter present within that pixel. So it's at this stage where our detection threshold comes into play. So we could, for example, color pixels in this image yellow that has any data that exceeds the detection threshold, or a percentage of the data exceeding the detection threshold. So this gives us a binary map of the area that we're trying to mask out. The next step, we would delineate contiguous regions of pixels that are above our threshold, and this gives us a number of blobs or potential areas that we would mask out from classification processing. We can remove, in the next step, we can remove some of the smaller blobs where we think classification is still possible. And then finally, we can, to make this practical for the field teams that are going to have to do clearance, we need to simplify the boundary. So the result here is a little bit unsatisfactory because you can see that inside this boundary there's a number of isolated anomalies on the periphery that can probably be classified as part of our final area. And one way to minimize this area is by applying filtering operations to the data image. So, for example, with the TEMTADS 2x2 sensor, we can filter the data image to be only sensitive to locations where multiple targets contribute to the data. So on the left, I'm showing observed data with 2 targets present and the locations indicated by white circles. On the right is a linear transformation of the data that is insensitive to the presence of a single target. So as we march those targets closer together, the filtered image on the right shows an anomaly at locations where multiple targets are contributing to the data. And so at 40 centimeters separation here, we get some maximum anomaly in our filtered image. And then as the targets get closer together, they effectively become a single target for the purposes of our modeling. And then when they're right together, the filtered image, they disappear from the filtered image. So this gives us a way of removing isolated anomalies from the image that we're working with. So if we apply that to that filtering approach to the Camp Hale data, we can see that the filtered image on the right reduces the relative amplitude of the isolated anomalies. So if you look at these red polygons that I've outlined, you can see some of these isolated anomalies have been really effectively removed from the filtered image. So we could now work with this filtered image when we do our image segmentation approach, and hopefully that's going to minimize the area that's getting masked out. Another more generic and generally applicable approach to delineating high-density areas is to carry out multi-object inversions over the entire area. And the rationale here is that we want to identify locations where our modeling is unable to reproduce the observed data. So a general rule of thumb is that we can typically handle up to 3 targets within the sensor footprint. So here we do a whole bunch of 3-object inversions in these small overlapping cells as indicated in this image on the right. And then what we do is we take all those 3-object inversions and stitch them all together. So here on the left, I'm showing the observed data. The middle plot shows us the observed data obtained with our 3-object inversions. And then the right image is the residual, or the difference between the observed and predicted. And it's that right image that we're interested in, because where there's significant residual, for example, exceeding our detection threshold, excuse me, those are areas where classification may not be feasible. So we can apply our image segmentation approach to the image on the right. So for comparison, here's three results of image segmentation or region finding on 3 different images. On the left, working with a data image, the middle working with that filtering approach, and then on the right, an image, a region identified working with the residual from multi-object inversion. And you can see the advanced approaches are slightly reducing the high density area that needs to be cleared, and they give us an objective way of doing this analysis. Okay, so that summarizes, or that wraps up the work on detection with advanced sensors. And I think time permitting, I'm just very quickly going to go through our work on risk assessment. So again, risk assessment in this context means verifying decision points as we go through our classification workflow. So one thing that we found very useful for risk assessment and verification in the risk assessment and verification in the target picking stage is what we call synthetic seeding. So what we do here is we take observed data acquired with our sensor at a site, and we synthetically, through modeling, place targets in the data. And then we use this combination of observed and synthetic data to test, for example, our target picking algorithm. So the figure on the left shows synthetic data generated by placing a regular grid of targets. It might be difficult to see on the left image, but then we can use that left image to pick targets and test whether our target picking algorithm and the parameters that we're using for our target picking algorithm are appropriate for the data that we're working with at our site. So you can see the picks indicated as white triangles in the middle image, and it's worked quite well in this case, but there is one target that we've circled in red that was actually missed with our target picking algorithm, which in this case is going to be a threshold-based pick. And so if we zoom in on that missed synthetic seed on the right, you can see that on that right-hand plot, I'm showing the track of the sensor as black lines, and you can see that there's basically a gap in the data coverage here, which has effectively reduced the threshold for that target in the observed data, and so it fell below the predicted threshold, which is assuming that we're meeting a particular line spacing objective when we collect our data. So in this case, we could either go out and recollect that line, or we can adjust our threshold based on the understanding that one of the data acquisition objectives has not been met for the data. So this is an example of how synthetic seeding can be used in the target picking stage. I would also mention that it's very useful for when we're doing screening. You can use synthetic seeding to get an understanding of the variability of polarizabilities, estimated polarizabilities for targets at your site, and use that to understand how you should screen targets on the basis of estimated polarizabilities. So that's an approach that's used quite a bit, I think, in conjunction with the dipole filter approach for screening. I'd like now to just turn to the end of the classification workflow and just one last point on risk assessment, and that is verification of the stop dig point. And so we can visualize the classification process here using the receiver operating characteristic on the right that shows classification performance up to the stop dig point indicated by the red marker. So at this point, the analyst has decided that based on their data processing, that they've found all targets of interest at that stop dig point. And so the question is, of course, we always have to verify, was that a good decision? How confident are we that we have in fact found all targets of interest at the end of our classification workflow? The obvious way to check whether we can stop digging is to really just continue digging on the dig list past the stop dig point. So ideally, as we proceed, with n additional digs past the analyst specified stop dig point, we're not finding any munitions, and so on the receiver operating characteristic, we're essentially obtaining a horizontal line. And so the question is, how many additional digs do we need to do to verify that stop dig point? And really, the number of additional digs is determined by regulatory considerations, and at the moment, the default is 200 additional digs for verification of the stop dig point. In this project, we initially approached this problem of verification digs before that regulatory framework was in place. So we also looked at statistical criteria for setting the number of verification digs. And I think this can still be useful in cases where we need to deviate from the prescribed 200 digs. So for example, if we're working at a site with not a lot of digs in the dig list, 200 might be too large. And so we might want to think about prescribing some percentage of the remaining targets as verification digs in our dig list. So we can come up with an objective number or percentage in this analysis, this statistical analysis, by modeling the process of ordered digging as a sampling process that's biased towards finding targets of interest. And in this framework, the number of additional digs is really dictated by the desired confidence level that you found everything and the probability that you can detect or that you can correctly distinguish targets of interest and non-targets of interest. So intuitively, the harder the classification problem, the more verification digs that you need to carry out. So in the example shown here, which is generated with a little widget that you can access at the URL shown at the bottom, we're considering a very easy classification problem where you've got a high probability of correct classification. And so in that case, the analysis is indicating that we'd have to dig for verification of the stop dig point about 48 of 1,000, or a little bit less than 5% of the remaining targets in order to verify this stop dig point. The key then in this analysis is then to have some objective measure of how well we can classify. And so to address this question, we've developed an overall measure that we call the data set degree of difficulty. And this measure combines metrics derived from both the observed data and the models that we estimate from the observed data. So we look at, for a site, as we're working with the site, we look at the polarizabilities that we've estimated for all of the targets, and then we compute some representative statistics that give us, we think, based on our experience, give us an indication of how difficult the classification problem is. And so that resulting metric, the data set degree of difficulty, is it's really primarily governed by, based on retrospective analyses, we found that difficulty is governed by how similar targets of interest and non-targets of interest are. That's pretty intuitive. And then secondly, how noisy the data are, so that's affecting our ability to reliably recover the polarizabilities. So in this plot here, I'm showing, or this table, I'm showing a ranking of ESTCP demonstrations in terms of the data set degree of difficulty. And then when we're working with a new site, we can generate a predicted data set degree of difficulty. So for this example, the row highlighted in yellow, we've got an indication that's a very difficult site. And so that indication can really help us to really guide us in our classification approach. And it can also help us to estimate a probability of correct classification for the sampling analysis that I showed in the previous slide. So I think I'll conclude there, and I think the take-home messages from the talk today are really the work that we've done on threshold analysis for advanced sensors. Again, all the threshold analyses that I presented today have been implemented in our detection modeler software and can really help to gain some insights into detection with advanced sensors and help as well, I think, for QC of some of the more advanced informed source selection methods. And then with risk assessment, again, I think the take-home message is we always want to test our decision points. So approaches such as synthetic seeding and statistical sampling for verification of the stop dig points can provide us with some tools to test our decision points. So I'll point you now to the project website for more information. There's some project reports online there. And please contact me by email or phone if you have additional questions.
Thank you so much, Lawrence. We've received a number of questions that we would like you to answer. Can you please let us know if the software for finding high-density areas is commercially available?
It is not commercially available. So that work is essentially has been described in the project final report. And so we'd hope that that will be, form a basis for implementation in the commercial software packages that are available for processing of detection data with advanced sensors.
Thank you. Can you talk more about how synthetic seeding can be used to test decision points?
Yeah, so I think as I mentioned, as I showed, it's very useful for testing your target picking parameters, and also what we found is very useful is at the screening stage to really understand what is the variability of parameters that we can expect to get for targets of interest. So for example, how fast will the polarizability for targets of interest decay when we're estimating those polarizabilities in the presence of site-specific noise. So that really helps us to adjust our cutoffs for target screening when we're doing informed source selection.
Thank you. What is the process if a target of interest is found during the confidence verification process?
That's a good question. I think you essentially, I think what you would do, and maybe Herb can comment as well, is you basically reset the counter. So if you're saying you need 200 verification digs after the last target of interest, if you find an additional target of interest, then you basically have to start over with your verification process.
Herb, would you like to weigh in?
No, what Lawrence said is correct. That's the recommendation in the CRAP template.
Wonderful. Lawrence, can you tell us if 200 is a good number of digs for verification of the stop dig point?
I think, as I mentioned, I think it's very much a question of what the regulators and the stakeholders are comfortable with. So the regulatory framework is 200, and I think that's what should be followed. And again, the tools that I presented today give you an objective way of deviating from that 200 if you need to. If for whatever reason 200 is for example, too many for the site that you're working at. But again, that all, 200 is a good number, and any deviation from that has to basically be agreed upon with the regulator.
All right. And a question from NASDAQ Southwest. On your estimating classification difficulty slide, you had a column for data badness. Can you define what that is, and does it correlate to poor correlation of data, noise influence, or other factors?
Yeah, I can't answer that question in a lot of detail. I just say that we have a lot of metrics that basically look at the noise on the data and combine different measures of the noise and their effect of their effect on estimation of polarizabilities. I would say that I believe in our second interim report that we provide expressions for all of the metrics that go into the data set degree of difficulty, so that analysis can be reproduced in, if you're using a different software. So it is just a metric that's related to noise on the data, but the specifics I'd refer you to an interim report.
Thank you. Can you tell us what are the costs for deploying the advanced sensors? Have you perhaps performed a cost analysis as compared to the cost for removing unintended targets?
I have not carried out an analysis, but I remember seeing, I believe Andy Schwartz from the Corps gave an analysis that showed the relative cost benefit of doing detection with advanced sensors. Maybe Herb, can you comment on that?
Yeah, absolutely. So I think the best source maybe to reference someone to would be the ITRC training that's currently going on, and you can find on the ITRC team website. And in that, they present a chart that, using what I think are pretty reasonable assumptions for an average site, and average site is defined somewhere on this chart that we're looking at now as Butner or MMR1, something with an intermediate DDD in Lawrence's words, where you can pretty easily correctly classify 80% of the clutters and not dig it. Using those assumptions and looking at the numbers there's a chart on the ITRC training, in the ITRC training charts. Anyway, the bottom line is about half the cost to do classification versus digging everything.
Thank you so much. Lawrence, based on your work, would you recommend that advanced sensors always be used for detection surveys?
No, I don't think I would make that recommendation. I think you have to do a cost-benefit analysis of whether working with an advanced sensor based on the anomaly or the target density at the site, whether that's beneficial. And I believe, again, other people have done that analysis.
Thank you. And we're going to take a few more questions before we wrap up here. What are the next steps for this work, Lawrence?
Well, I think the project is at an end. I think the one thing that's really necessary to do with the detection modeler software, we'd like to get in there functionality for the new metal mapper 2x2 sensor, which is essentially the same geometry as the TEMTADS 2x2 sensor and being manufactured by Geometric. So that should be a straightforward addition to the software, but I think it's important to get that in there. And then for further work, I think that would be the last remaining task for this project.
Thank you. And as we wrap up, and I'd like both you and Herb to weigh in, what would be the one takeaway that you would like to leave our audience with today? So we'll start with you, Lawrence, and then wrap up with Herb, please.
I think the emphasis in the webinar today has been just the tools for detection analysis. That it is a straightforward analysis and an extension of what we've done with conventional sensors like the EM61, but you can really get a lot of insight into how detection with advanced sensors will work when you're working on a munitions response project.
Herb?
So Lawrence won because he got to go first and he gave the real takeaway message from this webinar. Good job, Lawrence. But I agree with him. I think the thought that we should think about remediation projects with a target in mind and a depth of clearance in mind, and then design the survey around that, comes directly out of this work that Lawrence has done. And one thing that he didn't really show you is you may turn out that if you, let's go back to one of his charts that you maybe can keep in your mind. You say, I want to detect 37 millimeter projectiles to 3 feet. You use those, Lawrence's programs, and you're going to find out that's not doable with current sensors. So I think even at the planning stage, this can help you from writing down an objective which is unachievable and getting yourself in trouble halfway through a project. So both for correctly picking the threshold and keeping yourself out of trouble, these are very valuable tools.
Oh, great. Thank you both. Lawrence, you've done a beautiful job, and we're very grateful for your time in preparing for this webinar. Before we wrap up, I'd like to remind our audience that our next webinar is in 2 weeks on Thursday, February 23rd, and it will be on award-winning CERDP and ESTCP projects under the Resource Conservation Resiliency Program area. This webinar will feature Dr. Julian Alden from the University of Washington, who will talk about the hydroecology of intermittent and ephemeral streams, and he'll also discuss whether landscape connectivity can sustain aquatic organisms in a changing climate. Registration is already open for this webinar, so please visit the CERDP and ESTCP webinar webpage to register for this and other future webinars. I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. At this point, we would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you all for your time.